Okay, welcome to this first lecture on Prealgebra. And this lecture, we're going to be talking about exponents. Let me write that out here. Alrighty, exponents. And what are exponents? Well, I'm sure all of you know something called multiplication. Multiplication, well, I don't think I really need to explain that. But basically, exponents are repeated multiplication. Let's say I just wanted to multiply a bunch of threes together, a whole lot of threes. Okay, let's just say I have 7 threes here. Well, instead of writing all this out, which is a lot and takes a lot of time to do, what mathematicians decided to do was use exponents instead. So we're going to use this type of notation. We're going to put a 3 down and then put a 7 on the top in that little right corner over there. And what does this mean? The 3 means that you're multiplying threes. See all those? And the 7 means that you have 7 threes being multiplied together. Okay, so let me give you another example. Let's just say 2 to the 6th. Well, let's look at the bottom number. That means that we're multiplying 2's. And the top number, which is 6, means that we're multiplying 6 2's. So let's just write out 6 2's multiplying by each other. So that is 2 to the 6th power. All right. So let me give you a practice problem right here. What is 7 times 7 times 7 times 7 times 7? That's 7 to the what power? You can pause the video now if you want to try and do it yourself. And so basically the notation is, we already know we have a 7 here. And all we need to do is count how many 7s are being multiplied to each other and put that in the little box up there. So 1, 2, 3, 4, 5, 7 to the 5th power. Alrighty, so now we know what exponents are. Let's first look at a basic, like a sequence of exponents, a pattern. So let's just say we have 2 to the 1st. Well, this means we have 2's multiplying by each other, and then 1 means that we only have 1, 2. So that's just 1, 2. That's just 2. If we do 2 squared, well, that's just 2 times 2, because we have 2 2's multiplying by each other, 4. If we have 2 to the 3rd, that's 3 2's multiplying by each other, 8. All right? So what is the pattern we see here? If we go from this number to this number, what are we doing? Well, we're dividing by 2. If we go from this number to this number, what else are we doing? Dividing by 2. So for every number from left to right, we're going to divide by 2. So what is 2 to the 0 power going to be? Well, we're just going to divide by 2 again. 2 divided by 2, 1. 2 to the 0 power is 1. And the cool thing is, any number to the 0 power is always going to be 1. If you try the same kind of pattern out with, let's say, 3, or even -3, the pattern is going to come out to anything to the 0 power is going to equal to 1. Well, if we're here already, let's go further. Let's divide by 2 again. That gets us to the -1. Well, 1 divided by 2, 1/2. 2 to the -1 power is 1/2. Let's go on to the -2. Divide by 2 again, 1/4. Let's do it again, 2 to the -3, 1/8. So the thing is, if we raise stuff to negative powers, it doesn't mean that we're making the number negative. As you can see here, it's a pretty small number, but it's not negative. It's 1/2, 1/4, and 1/8. So what can we see here? Let's look at 2 to the squared again and compare this to 2 to the -2. Isn't this just 1? So if we have 4 here, isn't this number just 1 divided by 4? If you look at 2 to the cubed, we have 8. Isn't this number just 1 divided by that? So the cool thing we can realize here is that 2 to the -n power for some n, that's just 1 divided by 2 to the n power. Because if you can see here, 2 to the -2 is just 1 divided by 2 to the second power. And 2 to the negative 3 is the same thing as 1 divided by 2 to the third. All right? This is something that's important. Or we can even more further generalize this by taking out the 2's entirely and putting some random number a over there. So this works for anything. All right, so this is the first really important thing that we need to realize. So let me give you a problem here. What is 3 to the negative third? Pause the video and work it out yourself. So the first thing you might think here is, hey, 3 to the third is 27, right? So wouldn't it just be negative 27? No, no, no. I make that mistake a lot, and this is not a good mistake to make. We need to remember that a to the negative n equals 1 over a to the n. It's not just the negative of a to the n. So 3 to the negative 3 is just 1 divided by 3 to the third, 1 over 27. So this is the correct answer. It is not negative 27. Okay, so now we know what exponents are. Let's do some math with them. Okay, what if I just said I wanted to multiply 2 to the fifth times 2 to the third? Well, the thing we can do here is that there's a property where we can just add the exponents here. This would equal to the, okay? So what I did here was add these two, because I added the powers because we're multiplying 2 to the fifth times 2 to the third. Well, you may ask, why does this work? Well, let's turn 2 to the fifth into what it actually is. Let's expand it out to 5 2's multiplying by each other, all right? This is being multiplied by, well, what is this? This is 3 2's multiplying by each other. If we ignore the parentheses, let's get rid of these parentheses and multiply these two groups together. Isn't this the same thing as having 8 2's in total? We've got 8 2's. This is just 2 to the 8th. So what can we learn from this? If we're multiplying some a to the, let's use a different letter, x to the a times x to the b, well, that's just x to the a plus b power. This is a really important thing you need to know. All right? And what if we had more than just 2? Let's say we had x to the a, x to the b, x to the c, and x to the d. Well, we could add them one by one, but we can just use this thing and just add all of them in one go. A plus b plus c plus d. Okay? This is important. Okay, we got multiplication done. Let's now try some division. What if I took 2 to the 7th divided by 2 to the 4th? Well, when we multiplied, we added the powers. What if we subtract the powers with dividing? Well, that is correct. But why is this true? I just subtracted the powers and got the answer. Well, let me write out this again. 2 to the 7th is just 7 2's. Yeah, and then 2 to the 4th, 4 2's. And since we're dividing here, we can just cancel out these 2's, because 2 divided by 2 makes a 1, and a 1 doesn't change anything. So let's just take out these 2's. Oh, look, 3 2's left, 2 to the 3rd. So we took a total of 7 2's right here, and we subtracted the 4 2's on the bottom. Okay? So what is the generalized formula for this? If we have, if we have an x to the a divided by x to the b, this is just x to the a minus b. So let me give you an example right here. Let's see if you can figure this one out. What about 5 to the 17 divided by 5 to the 19? Okay, so we used the property we just learned and we're going to subtract 19 from 17. This is 5 to the 17 minus 19 power. That's just 5 to the negative 2. All right? And let's go way back into the beginning where we learned about what negative powers are. Is this negative 10? No. Is it negative 25? No. It is 1 divided by 5 to the second power. 1 over 25. So this is the answer. And usually when you're doing math tests and whatever like that, you don't really want to have a negative power anywhere. It's always best to turn it back into something like this, where you have positive powers. So combining what we learned, let me give you a pretty difficult problem here. What is this? Give you a few minutes to work it out. And the first thing we can do here is, well, let's just pretend that none of this is here. All right. So what we can do is we can just add all of the exponents on the top because we're just multiplying them, right? So on the top we have 3 to the 7 plus 5 plus 7. And what is that? That is, do some quick addition, 3 to the 19. And now let's pretend the top doesn't exist and just focus on the bottom. The bottom, using the same property we learned, is 3 plus 6 plus 7. 3 to the 8 plus 6 plus 7 power. Okay, and what is this? This is 3 to the 21. So 3 to the 21 goes on the bottom. See what I did there? And finally, we can use the exponent division property, see how this is 3 to the 19 minus 21 power. And what this is 3 to the negative 2, 1 over 3 squared, 1 over 9. Okay, but this method is actually not the best way to do it. I'll show you once I get this out of the way. So what is the best way to do this here? Well, the first thing we can notice is that we have a 3 to the 7th on the top and a 3 to the 7th in the bottom. When they divide each other, they make a 1, so we can just get rid of them entirely. We don't even have to worry about them. So these guys are gone, right? And we don't have to add these and subtract these separately. We can actually just add them all and subtract them all in one go. This is the same thing as, so we're gonna just add all the stuff on the top, right? And this works because we're just multiplying exponents, right? And we're gonna subtract the sum of everything on the bottom. We're gonna subtract everything down here. So I'm gonna subtract, we're gonna subtract the sum of 8 plus 6. Okay, so let's look at this again. We added 7 plus 5 because they're on the top. And we subtracted the sum of 8 plus 6. This is basically what we were just doing, but all in one step. So let's take the negative out. So the generalized case we can see here is that we're going to add all the exponents on the top and subtract all the exponents on the bottom. Again, we can just do this, and that's 3 to the negative 2. All right, let me give you another example here. 5 to the 8. Okay, so first thing we can notice is that there are two 5 to the 8s on the top and bottom. Get rid of those immediately. And now we're just going to add everything on the top and subtract everything on the bottom. Or in other words, we add all the powers in the numerator and we subtract all the powers in the denominator. 5 to the 7 minus 12 minus 3, which is 5 to the negative 8, I think. 1 over 5 to the 8th, and I don't know what 5 to the 8th is, and we'll just leave it as that. So now what else can we do with powers? Let me do something really weird here. And let me take 3 to the 5th, 2 to the 3rd power. How are we going to do this? Well, let's first expand out 3 to the 5th into multiplication. We have 5 3's multiplying by each other. All right? And we're taking this whole lot and raising it to the 3rd power. So what does this mean? We're multiplying all of this 3 times. So we're going to have one group of 3 times 3 times 3 times 3 times 3, another group of 3 times 3, another group. Well, how many 3's do we have total? We have 3 groups of 5, 15 3's. So basically what did we do here? We multiplied these powers. So when we have a power to another power, we multiply the powers together. So let's generalize this as a to the some n power to the m power. We multiply the powers to get our final answer. Okay? Important, important, important. And let me give you an example right here. What about 3 to the 6 to the 9? Give you a minute to figure this out. You can pause the video. And so using the formula we just used, we're just going to multiply these two together. 3 to the 6 times 9, 3 to the 54. Yeah, 3 to the 54. All right. So now we're going to get into the more difficult stuff. So what if I give you something really weird, like 4 to the 6th, 25 to the 6th. Well, this thing is probably going to be really hard to figure out, and this thing is also really hard to figure out. So what I'm going to do here is actually, since they're to the same power, I can put them together. I can directly multiply these two bases, 4 times 25, and put them all to the 6th power. So if I do this, this is just 100 to the 6th power. And what is this? 10 squared to the 6th power. Because 100 is still a little abstract to me, and I really like stuff to be in tens. So 10 squared to the 6th power, 10 to the 12. So this number is just 1 with 12 zeros after it. All right. And I don't think I wrote 12 zeros there, but whatever. So the cool thing you can do here is if you have two numbers, n and m, to the same power, we can combine these to n times m to the same power. Okay? So this is especially useful if you have problems like these. All right? Because, okay, I'll give you a little time to solve this problem. You can pause the video if you want to. And, okay, so I don't know what 2 to the 17 is. I also don't know what 5 to the 17 is. But since they're to the same power here, I can just multiply these together to get 2 times 5 together to the 17 power. All right? So what is that going to be? This is going to be 10 to the 17, 1 with the 17 zeros after it. Dot, 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 dot. Okay? So I don't even need to multiply these things out to get my final answer. So let me give you another problem for you to solve. 2 to the 15, 5 to the 13. Pause the video if you want to solve it for yourself. Okay, so the first thing I see here are 2's and 5's. I want to make a 10, right? But the problem here is we don't have the same number on the top. Well, what can we do here? Well, we do want to combine them, but we can't just do it as it is now. So what if I did this? I turned the 2 to the 15 into a 2 to the 13 and a 2 squared, because these two will turn into a 15 in the end, right? This is the same thing as this. And then I just have a 5 to the 13. Well, now I have this one and this one. I can combine together because they're to the same power. So what I did here was I turned this 2 to the 15 into 2 to the 13 times 2 squared so that I could combine this with the 5. Okay, so in the end I can just combine these right now, 10 to the 13 times 2 squared. And what is 2 squared? That's just 4, and 10 to the 13 gives us 13 zeros here. Whatever, dot, dot, dot. Okay? This is a clever manipulation we can make here. Instead of just multiplying these out because they're not the same, I can change it so that it makes the same. And similarly, what if I gave you a problem that was like 50 to the 5th divided by 5 to the 5th? If we did it with multiplication, I think we can do it again with division. So we can just do this, 50 divided by 5, all to the 5th power. So just like with multiplication, we can put all of these numbers under one exponent right here. And if you want to see this work in a different way, we can rewrite this guy as 50 to the 5th times 1/5 to the 5th. See that? And let's just pretend these two are multiplying by each other. So then we just have 50 times 1/5 all to the 5th using the multiplication property we used, and voila, we have the same exact thing as we have right here. Okay? And solving this, we get 50 divided by 5, which is 10 to the 5th. Okay, so we can do a similar thing with division. So what if I gave you 100 to the 5th divided by 50 to the 5th? Pause the video and try to figure it out yourself. And now I can just put these two numbers under one exponent because they're going to the same exact power. And what I get is 2 to the 5th, 32. Alrighty, here's another practice problem for you. What if we did 49? Wait, let's do 45 instead. 45 squared, 2 squared divided by 30 squared. This time we're going to use multiple aspects of using both the multiplication and the division here. So let's first combine the two on the top because they're to the same power, right? This is just 45 times 2, all to the second power. Don't forget that 30 squared. Okay, and then 45 times 2 is 90. 90 squared over 30 squared. And now we're going to put 90 and 30 under the same exponent because they're going to the same power. It's just 3 squared. 9. All right. So that is all you need to know. So let me give you some practice problems here. What is 2 to the 7 times 2 to the 9? We're going all the way back to the beginning now. Well, we just add these two things together. 2 to the 16. All right. And what if I did 2 to the 7th divided by 2 to the 9? Well, I just subtract these. 7 minus 9, 2 to the negative 2, 1 over 2 squared. What if I did 2 to the 7th to the 9th power? Well, we use our power to a power formula and realize that this is 2 to the 7th times 2 to the 7 times 9 power. Okay? So let's move on to something a little more difficult here. What is 4 to the 7th times 25 to the 8th? Okay, let me figure this out. Well, the first thing I see is 4 times 25 is 100. So somehow I'm going to try to put those two things together. But right now, I can't yet because they're not the same exponent. So what can I do? Well, again, I take the larger one and I can split it so that I can match this with the 4 to the 7th. I already have a 4 to the 7th. I want to make 25 to the 7th so that I can combine these two together. So all we have left is a 25 to the 1st. And now I'll combine these. 100 to the 7th times 25. And instead of writing 100, I'll write 10 squared because I like 10. That's 10 to the 14 times 25. So that's just 25 with 14 zeros after it. Dot, dot, dot. All right. I'll give you another problem. What is 2 to the negative 9, 2 to the 17, divided by 2 to the negative 18, 2 to the negative 7. This is a little tricky here. So using all the properties we know, we just add everything on the top, subtract everything on the bottom. 2 to the negative 9 plus 17. I'm going to have to subtract negative 18. We're going to have to subtract that, which is the same thing as adding 18. We're going to have to subtract negative 7, which is the same thing as adding 7. All right? So once we have this is pretty easy to do. I think this is 33. I might be wrong. Okay. So now, here is a challenge problem for you. Can you write 2 to the 6th times 4 to the 7th, 8 to the 8th, 16 to the 9th? Can you figure out what this is? Okay, so right now I can't just add 6 plus 7 plus 8 minus 9 because they're not all the same base. Somehow I have to get all of these into the same base. Well, what I can notice here is that 2, 4, 8, and 16 are all powers of 2. 2 is 2 squared. 2 is 2 to the first power, I mean. 4 is 2 squared. 8 is 2 to the third. 16 is 2 to the fourth. Okay, so I can represent all of these numbers as powers of 2 now. So let me rewrite this as 2 to the 6th times 2 squared to the 7th power times 2 to the third to the 8th power divided by 2 to the 4th to the 9. All right, and now we can use the power to the power formulas to figure out that this is 2 to the 6th times 2 to the 2 times 7, 14, 2 to the 3 times 8, which is 24, and divided by 2 to the 4 times 9, which is 36. And then in the end, we'll turn this way and we'll just do adding everything on the top and subtracting everything on the bottom now, because now we have all of them in the same base. 6 plus 14 plus 24 minus 36. And you can go ahead and solve that yourself. But this is the answer. So now we're going to talk about something that's really advanced, something that you might see on math competitions. And this is a question that they always ask a lot. And it is, how many zeros are at the end of some number? Okay, or they could write how many trailing zeros. So for example, if we have this number, we have 5 trailing zeros. If we have 3 trailing zeros because they're at the end. This zero doesn't count though. So how would we go ahead in solving this kind of problem? Well, let me give you an example right here to figure this one out. Let's do 4 to the 6th, 25 to the 18. Okay, so how would you figure out how many zeros are at the end of this thing? It's kind of a very abstract idea. Well, one thing we can notice is that whenever we multiply a number by 10, let's just say 10 times 24, we literally just put a 0 at the end of 24, right? If we do 10 squared times 24, we put 2 zeros at the end. So it seems like the amount of zeros we have here at the end of a number is how many powers of 10 it has. So basically, again, let's take out my number here. Okay, so again, let me figure out how many 10s we have here. I have a 4 and a 25 here. So I can try to multiply these together. But first, I need to figure out how to get these two into the same power. So right now, I can't add them just yet. So what do? I turn this 25 to the 16 into a 25 to the 9 times 25 to the 7. Because this way, I can combine this to make 100 to the 9. Right? Well, let's first look at 25 to the 7. This one has no multiples of 10, no powers of 10 inside it. And so this doesn't contribute to any zeros, so we can just remove that entirely. All we need to do now is focus on this 100 to the 9. Well, what is this? This is just 10 squared to the 9 power, 10 to the 18. So how many zeros do we have? 18 zeros. So let me give you another problem here. So we have 7 to the 417, 19 to the negative 6, wait, to the 17, 4, 6, 2 squared, and it was 25 to the 16. How many trillion zeros are there in this? Maybe you can pause the video now and take some time to figure this one out. So what we need to do is figure out how many powers of 10 there are in this number. For one thing, we can just get rid of these things that don't contribute anything to powers of 10, because 10 is 2 times 5. We're looking for powers of 2 and 5. So we can get rid of 7 and 19 definitely. Let's get rid of this one. They don't even count. Why didn't we get rid of 4? Well, we can notice that 4 is just 2 squared. 2 squared to the 6th is 2 to the 12. If we combine this with 2 squared, we get 2 to the 14. All right? So the number we're finally looking at here is 2 to the 14, 25 to the 16. Okay? So 2 times 25, that's 50. Well, we don't really want 50. We want powers of 10, right? So what can we really do here? Well, we can go 2 directions in it. So first, we know that 2 times 5 is 10. We're going to try to make this 25 into a 5. So we can do that by realizing how 25 is just 5 to the 2nd power. So this thing is the same thing as 20 times 5 squared to the 8th. See that? Oh, sorry. 5 squared to the 16. Because 5 squared is 25. This is just 2 to the 14 times 5 to the 32. So now we can do all the stuff we need to do to figure out how many powers of 10 there are in here. So let me put this here. 2 to the 14, 5 to the 32. Can we combine them just yet? No, we can't. We need to get these two to be the same so we can push them together. And so I want to get this 2 to the 14 to combine with a 5 to the 14. And what do I have left on this side? Well, it's 5 to some power, right? But this is useless because this can't make any powers of 10. So we don't even need to care about that. So all you have left is 2 to the 14, 5 to the 14, combine them together, 10 to the 14, which is 14 zeros. All right? What if I went the other direction? Let me first get rid of all this stuff. We can also go the other direction. We can realize how 4 times 25 is 100. So what if we turn this 2 to the 14 into a power of 4? Well, this is just 4 to, wait, rewind a little bit. This is just 2 squared to the 7 power, because 2 times 7 equals 14, which is basically 4 to the 7th power, because 2 squared is just 4. So in the end, we have 4 to the 7th times 25 to the 16. Let's move this up here again. 4 to the 7th, 25 to the 16. Well, I want to combine these, but we can't combine them right now because they don't have the same power. But I'm going to change it so that we do. So we still have a 4 to the 7th, but we're going to turn this 25 to the 16 into a 25 to the 7th times 25 to the 9, right? So we're going to get rid of this 25 to the 9 because that doesn't give me any zeros, because this ends in 5 anyways. So let's combine these two together. 100 to the 7th. That's just 10. That is just 10 squared to the 7th. 10 to the 14. So we get 14 zeros as our answer once again. So to summarize, let me write out some of the formula here. If we have n x's multiplying by each other, this is x to the n power. Okay? If I have some x number to the a power times an x to the b, this is x to the a plus b power. If I have an x to the a divided by x to the b, this is x to the a minus b power. If I have x to the a to the b power, that's just x to the a times b power. Okay? And the last tricks we can make here are, if we have some a to the x power and the b to the x power, I can combine them to make ab all to the x power. And similarly, I can do this with division. All right, so this is basically a summary of all the formulas. And one last thing you need to remember is anything to the 0 power is 1. And let's just say x to the negative n. Remember that is 1 over x to the n and not the negative of x to the n power. And so that is really all you need to know for pre-algebra exponents. So thank you for listening, and I'll see you next time. Goodbye.